Up to this point, we have discussed that corrosion is an electrochemical process because the anodic and cathodic reactions can occur in separate regions, and we have seen how we can represent a corroding surface in terms of electrical currents. Additionally, we have seen that applying a current in the anodic direction relative to the structure increases the rate of oxidation, while applying a current in the cathodic direction reduces it. Now, in this lecture, we will examine how we can physically measure the potential of a structure, and this will enable us to begin understanding the relationship between potential and current and what this means in the context of cathodic protection. Let's start by looking at how we can measure the potential of a structure that is undergoing free corrosion. The process in itself is quite straightforward because all we need is a reference electrode, a voltmeter, and some cables to make the connections. Now, to take the measurement, we place the reference electrode in the environment and connect the cables of the reference electrode to the common terminal of the voltmeter. Then, using another cable, we connect the positive terminal of the voltmeter to the structure. The voltmeter will now display the potential difference between the reference electrode and the structure. Now, the reference electrode essentially acts as a half electrochemical cell that contains a metal and an environment that are housed in a suitable container, such as to establish a known and stable equilibrium at the metal surface inside the reference electrode. This known and reliable potential value remains consistent regardless of the surrounding environment. So, importantly, for the potential measurement to be reliable, the reference electrode must be electrically connected to the environment in which the structure is immersed. So, to maintain this connection, the reference electrode typically includes a porous membrane made out of porous material at the bottom that is soaked in the electrode's electrolyte and is also in contact with the environment. This allows the ionic movement between the environment inside the reference electrode and the environment outside the reference electrode. So, the solution inside the reference electrode remains constant and therefore the potential is stable, but is electrically connected to the solution outside. As an example, in a copper-copper sulfate reference electrode, the internal metal is copper, and the solution inside the reference electrode is a saturated copper sulfate solution. So this setup creates an equilibrium between the oxidation of copper to form copper 2 plus ions and the reduction of copper 2 plus ions to form metallic copper. And this produces a well-known potential of plus 0.314 volt versus hydrogen reference electrode. The hydrogen reference electrode is another type of reference electrode, but it's a bit more complex to realize in practice, so is not used very commonly. Nonetheless, the hydrogen reference electrode serves as a fundamental reference because it has been assigned by convention the value of 0 volt, so all the other potentials are normally referred in thermodynamic tables with respect to the standard hydrogen reference electrode. Now, regardless of the reference electrode that we are using, when we take a measurement as described in this sketch, the reading that we would get from the multimeter would reflect the potential of the structure with respect to the reference electrode used. This measured value of potential is the corrosion potential of the structure, and it corresponds to the potential where the value of the anodic current equals the value of the cathodic current. And this depends both on the nature of the reaction, so on the nature of the structure, on the material that forms the structure, and on the type of cathodic reaction, but also on their kinetics. So now that we know how to measure a potential, let's start examining the kinetics of the reactions that might be involved in a cathodic protection scenarios. So, Effectively, the kinetics of a reaction can be represented on a potential versus logarithm of the absolute value of the current density diagram. So, if for now we focus on the oxygen reaction, the equilibrium potential will be at a specific point here in this diagram, where the rate of oxygen evolution equals the rate of oxygen reduction. Now, for the purpose of cathodic protection, in a cathodic protection scenario, we are mainly interested in the oxygen reduction reaction as a cathodic reaction. So we are interested in the behavior of the curve below this point. So if we ignore for now the reaction of iron oxidation, the portion of the curve that represents the cathodic reaction of oxygen reduction initially exhibits a linear dependence of potential on the logarithm of current, and in this region the reaction rate is not limited by diffusion. So the rate determining step in this part of the curve is the charge transfer to form OH- ions. However, as the potential continues to decrease, the current reaches a limiting value, and this is due to the limited rate at which the oxygen can diffuse towards the metal surface. So, in this region, the current becomes independent on the potential and is controlled by the rate of oxygen diffusion. Now, let's look at the other reaction, which is the iron oxidation reaction, so we just ignore the oxygen reduction reaction. So, if we are applying an anodic current to the structure, we are increasing the potential of the extraction, the current associated to the iron oxidation will increase. Now, in this case, the iron oxidation reaction is not limited by diffusion, because there is plenty of iron on the structure and the environment can accept plenty of iron ions. So the current will increase exponentially with the potential. And this appears as a straight line in this semi-logarithmic plot. The point where the two lines intersect represents the equilibrium for the corroding metal surface. And this is the point where the anodic current of iron oxidation equals the cathodic current from the oxygen reduction. The current associated with this intersection point is the corrosion current that is flowing between the cathodic and the anodic regions inside the metal and between the anodic and the cathodic regions inside the electrolyte. So, from this potential versus logarithm of current plot, we can observe that the corrosion current, in this case, corresponds with the limiting oxygen diffusion current as we already discussed. Now, let's relate this to the case that we discussed in one of the earlier lectures, where an external current was applied anodically to the right electrode and cathodically to the left electrode. So this setup results in an increasing anodic current on the right electrode and in a reduced anodic current on the left electrode. Consequently, the potential of the right electrode will be higher than the corrosion potential, while the potential of the left electrode will be lower than the corrosion potential. So, we've learned that in general, applying a cathodic current reduces the rate of the anodic reaction and lowers the potential. On the other hand, applying an anodic current increases the reaction rate, the anodic reaction rate, and increases the potential. Therefore, if we reduce the potential of a structure, this will lower the corrosion rate because it will decrease the anodic current on the structure. So, to summarize, in this lecture we have seen that we can measure a structure's potential in contact with an electrolyte using a reference electrode and a voltmeter. The reference electrode is a purpose-built half cell that provides a stable potential regardless of the environment that is contacting. At free corrosion, the surface of a structure supports both anodic and cathodic reactions. The kinetic of the cathodic reaction includes an initial region where the potential varies linearly with the logarithm of current, and then, as we go down in potential, there is a diffusion-limited region where the current is constant with potential. The anodic reaction of iron oxidation, on the other hand, shows a linear behavior on these semi-logarithmic plots. The corrosion potential is determined both by the thermodynamics and by the kinetics of the reactions, and it coincides with the potential where the anodic current equals the cathodic current. Applying an external current to a structure in the anodic direction increases the anodic current on the structure or on the electrode and increases its potential. While on the other hand, if we apply a cathodic current to a structure or an electrode, the anodic current decreases and the potential decreases. In cathodic protection, the current of course is applied in the cathodic direction and therefore is always associated to a decrease in the structure potential.